we'll go ahead and get started. There we go. Cool. So welcome to the community call, March edition, 2022. I can't believe it's the year 2022, but it is. Here we are. We got a couple things today, and I think we even have a fancy presentation. We're going to talk about the metrics generator, and we have some good news in that. I think that will be in 1.4, which should, I guess, maybe we'll target for next month. Or is it this month? I don't know. I'll go back and look. We generally do every other month, and maybe that's next month. And then we have some backend search news. I was mentioning that earlier, but I really feel like we crossed a hurdle. We added a couple features there that have seriously increased query times. And then I think we have one more coming soon, and 1.4 is going to see way faster search speeds. And Marty and Ananya can talk about some of our Parquet work. We continue to hammer on Parquet. It's a very promising technology. I don't think we're quite ready to commit to it yet, but they have some great metrics and insight information to share, kind of what we found as we have taken it apart and try to use it to store traces. So I don't really know, but I think metrics are first. Is that right? Oh, before we get into it, feel free to put any things in the agenda doc. And then also, you're welcome to jump in with questions, either in chat or you can unmute and ask questions. This is very casual. We do have this fancy slide presentation thing, but this is a conversation. Don't be afraid to jump in and ask what you need to ask, and interrupt whoever's chatting. So with that, I think, is it metrics first, Kunrad? Is it you?
Yeah.
Cool.
So I'll start out by talking a bit about the metrics generator. We already discussed this a couple of times in previous community calls, so this would just be like an update and share a bit of like the performance we're seeing in our internal clusters. So I think last time we discussed the design document, and going further from that, we have now also merged the metrics generator code into the main branch, so you can run it already if you like dare to run the latest commits from Tempo. We run it internally and it's been going pretty good, but we're doing a lot of improvements at the moment. I just wanted to do like a quick recap of the architecture. So how the metric generator works is we're adding this new component next to the ingester, which will receive a second asynchronous request from the distributor. So the distributor will write to the ingester first, and then it will do an async request to the metrics generator. And it also has a ring to do load balancing. And then the metrics generator will process the incoming spans and write metrics to Prometheus. So this didn't really change since the last community call. I also have an architecture diagram of the internals of the metrics generator, and that's kind of moving around as we discover stuff and figure out better ways to design this. So this is kind of the architecture we are ending up with now, and it feels like a very good base. And so what it looks like internal is you have kind of this pipeline from left to right, and there are kind of like three modules or stages in this pipeline. So the first step in this is the processors. So the metric generator receives all these spans that are being written to Tempo, and we use these metrics processors to convert the spans into metrics. So the processor can, for instance, count how many spans there are with an error, and we'll just keep updated metric, oh yeah, I saw a span with an error, okay, +1, and then again that all the time. And the processor will then update the metrics and store them in the registry. We intend to make the process kind of dynamic, so you can change them at runtime. You can add processors, you can disable them, and you can also change the config in them. Right now, you can only enable and disable them, but we also want to make some configuration dynamic, so you can adjust them on the fly in case you're generating too much metrics or too many series and stuff like that. And we currently also have two processors. We have the service graphs processor and the span metrics, but we want to design it in a way that's easy to add more processors. So if you have some use case in mind, it should be easy to write a processor for that. So the next step in this is the registry. And the registry is this store of metrics. So it just keeps track of all the metrics that are like generated by the metrics generator. So the processor uses the registry to store the metrics, and it will always like update them, increment them, or like do whatever. The registry will then scrape itself, kind of like Prometheus scrapes other instances. It's a similar operation. So it just gathers the state of all the counters in the registry, and then it writes a sample to the storage layer. And in this registry, we can also enforce limits on the amount of active series and some other properties. And then the final step in this pipeline is the storage layer. And what this does is it will buffer the samples as they get written to the downstream time series database. So we will be using the Prometheus remote write protocol to send metrics to, for instance, Prometheus, Cortex, or whatever other database supports this protocol. And the storage component will buffer samples before sending them, and it will also handle retry logic, queuing, and those things. What's actually pretty fun is that we didn't write this ourselves, this whole storage component with a wall. We're using the Prometheus agent. So the Prometheus agent is like a specific mode to run Prometheus, which is has like a minimal wall implementation without the querying and alerting capabilities. It's just a wall to store samples and to remote write them. And we were able to just use that code directly, plug it into Tempo, which is really cool because this is like a very good implementation which has been battle tested already. And it will also operate the same as Prometheus. So you have the same metrics and the same behavior as if you would be running a Prometheus instance. Yeah, and that's kind of like the architecture we have right now. So we still have like a couple of PRs up to get this into place, but it's like slowly getting like shape. And then I can also share some performance stats. So we've been running this in our internal clusters for like 1 or 2, maybe 2, 3 weeks, I guess. And I can already share like some stats from what we have observed already. So the first thing that we observed is by adding the metrics generator, the distributor will have to do more work, right? It has to send the second request to the metrics generator. And we saw that this currently especially has a high impact on the CPU. So we saw like a 30 to 40% increase in CPU usage across all the instances. And this is caused by the extra work that we have to do. We have to send a second request. We have to marshal this request again and then buffer it for a bit and stuff like that. We think we can still optimize this a bit by doing some better buffer logic. So Mario made a PR for this. And a next step might be to use like a data format which is easier to serialize, which is like less CPU intensive. Currently, we use OTLP directly, which is a very rich format with a lot of nesting, which is nice to express traces, but we don't necessarily need this richness to implement the metrics processors. So there might also be an option to improve this further. So we hope to bring this down by the time of Tempo 1.4, but we'll see how far we get. And then what we also saw is, like resource usage for the metrics generator itself. So the largest deployment that we have it running in right now is a cluster which is ingesting like 1.2 million scans per second, about like 200 megabytes per second. And we can handle this load by running 8 metrics generator next to each other, so like just 8 replicas. And this is, I think, about half the amount of distributors and like a third of the amount of ingesters. So this component is already proving to be more efficient than the distributor, which is nice, because then you need less instances. And yeah, in our cluster was like consuming about 2 CPUs and like 1.6 gigabytes of memory. So just to kind of give like an idea of what this uses. We noticed that the CPU usage is correlated with the amount of spans we're ingesting, but memory not so. So CPU usage is expected because if you ingest more spans, you have to do more work to deserialize the data, to unmarshal the protobuf. So if you go up, like we notice if you go higher, then the instance starts to struggle and starts to crash and stuff like that. But memory is not really impacted by the amount of spans you ingest. So that's also nice because that means that we can optimize the code a bit more so it's more CPU efficient. But memory is not like a big issue right now. Like it seems okay. And then, oh yeah, and then what I can also share is an issue with generating metrics from traces is that traces are typically, they have high cardinality, right? You can have like a lot of span names, a lot of different tags within your traces. And when you instrument your code, you might not be thinking about cardinality. Like you might not consider that you shouldn't add like a random number into your span name. That can happen. And by generating metrics from traces, we have this risk of just causing too many series, which would like bring down your time series database. So something we're working on is also adding controls to limit the amount of active series we're generating within the generator. And I have two screenshots here showing the amount of active series in the generator. And the first one is without any control. So this would just, every time there's like a new span coming in with new data, we would start a new series, like a new time series. And we would just keep sending them all the time, which would mean if this instance runs for multiple days, this number always increases. So you can see this always goes up. It starts at like 10,000 and then goes up to like 15,000, 20,000, and you just keep sending all these time series all the time. And then what we've now integrated into the registry is the ability to drop stale series. So this means a series that hasn't been updated in like 15 minutes. Then you just delete it. You stop sending it. And then you get like a nice, like a flatter line and a more stable system. So this is one way to kind of deal with the cardinality is like, if there's a spike in cardinality, there will be a moment in which there are more active series. But after a while, it goes back down again when these series stop being updated. A second thing we're adding is also the ability to set limits. So you can, for instance, limit the generator on like, hey, you can only emit 10,000 active series. And when there's like one more, you just stop. You don't generate like a metric for that. And so that would be like a hard stop to protect the downstream database or like the bill you're paying for it. Yeah, and that's kind of it for what I have for the metric generator. Yeah. So yeah, I think we have like a couple of big changes coming in like next week, in the next 2 weeks, and then we should be at like a very good spot to release this with Tempo 1.4. So we'll probably be working more on like documentation and sharing some like operational information, alerting, stuff like that.
Cool. Go back a few slides to your metrics. One of your distributors hit 40 gigs of working set. Is our limit really over 40 gigs? How did that not boom? What happened there? Do you know?
Yeah, I don't know. I didn't really look into it. I thought it was just like something due to the rollout. Maybe it's the bucket, like that didn't match well.
Sure.
Because I don't think they can get like 40 gigs. Yeah,
No,
I'm
they
not sure.
can't. I'm 100% sure. I don't even, yeah, our nodes would handle that, but they'd boom well before that. I don't know what our limit is, but there's no way it's over 40.
Yeah.
The other thing that's really cool is, do we know what the ingest rate is in terms of like spans per second or something? Because 10,000 active series for what I believe is 1,000,000 spans per second is really cool. And
Oh yeah. So these graphs are now from the million spans per second cluster. So this is from a smaller cluster. But yeah, in this cluster in which we were ingesting like a million spans per second, I think we had like closer to 100,000 active series. And we noticed that it would also increase all the time. So it started like 100,000. And if you run it for like a couple of days, it goes up to 500,000. So every instance is sending 500,000 active series, which is just too much. But yeah, like we still have to kind of figure out this ratio between the amount of spans ingested and amount of active series. Like the connection, it's not always correlated. It could be if you're sending like a lot of spans, but they're all of the same system, you might have a small amount of metrics. While
Of
if you're
course,
sending
correct.
a couple of spans with like very high cardinality, you might be generating like a ton of series. So that's something interesting that we'll have to kind of learn how it works.
And like sort of, we'd have to do some sort of analysis to figure out which active series are just enough to create the kind of dashboards and graphs we need, like the red metrics and so on, and then sort of maybe work backwards and see if we can reduce stuff. But really cool.
Yeah.
Like, this is really cool and very exciting.
Yeah, I think that's something we should also explore. Is currently the processes just process all the spans like without filtering. I think we could add filtering capabilities to like say, don't process spans from these services because we're not interested in those, or like drop spans with like that don't have a specific tag or whatever. And it would also be a way to keep the amount of active series down, so you only generate metrics for the interesting spans. Yeah.
Cool. I think there's another cool thing about this, and you can add per tenant overrides, right? And you can specify which labels you want to be recorded as series and stuff. I think that's also really powerful and like another cool feature. Nice.
All right, cool. I think we can move on to the next part of the community call, which is backend search.
That's me. Yeah, backend search. So we're going to talk a little bit about some of the settings or tunables for search and what we have. I'll share kind of our internal settings there, as well as some new ones coming out in 1.4. So we'll talk a little bit about what's in 1.3.2, which is out now, and then what we've changed in 1.4, and what kind of performance we're seeing because of those changes. I'll share some internal metrics, kind of like Kunral did with the metrics generator. So, given our spans per second, like what kind of rates of search are we seeing? And then we're going to talk about Grafana Cloud traces a little bit. Coming soon. It's already actually turned on for a handful of customers. If you're interested in this feature and you're using cloud traces, you're welcome to ask me in this call or DM me in Slack. I'll turn it on for you as well. And then across the board, we're targeting the week of March 21st. We have some things we need from the hosted Grafana team. They need to set a feature flag for us, and they're working on how they're going to do that. So I think about the week of 21st, we'll finally have this enabled in cloud traces for everyone, which means everyone will have this full backend search experience. Well, my bad, if you're in Google Cloud, which almost all of our customers are. And then we're looking to roll that out to other clouds, probably in the next few months. So yeah, we can move forward. So in 1.3.2, we've kind of shared this diagram before, but you have the query front end. A query comes in and it's broken up into thousands of jobs, which the queries then do their best to service. And they also pass these, and then you can also configure it to use serverless, which is what we do given our volume. So in 1.3.2, the query acts as a proxy for serverless. Basically, the query front end makes 30,000, not that many, thousands, 3,000, 4,000 jobs. The queryers consume those jobs one at a time. They pass those onto the serverless functions, which then service each one at a time. And I've highlighted some settings. If you look in our docs, under the operational section, there is a doc that outlines actually everything you're seeing here, but I'll just talk about it real quick. We need to just make some adjustments. You'll notice we've changed the server timeouts, the HTTP timeouts. We're still kind of operating relatively slowly, not as fast as we want, but we're improving. And then the concurrent jobs and the maxed outstanding per tenant just lets you push a whole lot more through the query front end. The defaults in the query front end are still kind of tuned for trace by ID search. We might want to actually update that and make the defaults work with just search generally as we've built now. But the important ones are like the target bytes per job, which will which will divide your entire search job into individual jobs. I'm sorry, your entire search request into individual jobs that are about, in our case, 10 megs each, which are then served by the queries or the serverless functions. And then you can see some other options on there. Concurrent jobs and max outstanding per tenant just allow the query front end to create way more jobs than it would normally for your queries to service. And at the query level, the search external endpoints is what actually tells it to use serverless. And the max concurrent queries, by default, the max concurrent queries is like 2. Again, everything is tuned for trace by ID search. But if your queries are only doing 2 at a time each, that's not going to do you any good. You need them to do way more. So we have that set to 100 right now in our largest cluster. So each one, and since they act as a proxy, they actually don't do much work. They just take a query and instantly shove it into the back or to the serverless, and they could really do more than 100 at a time. They're not really doing much of anything except proxying. If we move forward. So 1.4.0, we've added a few settings that are really kind of changing the rate at which we can search the backend quite a bit. One is we added hedging to the query front end actually just yesterday or something. In fact, it's kind of embarrassing that it took me this long to add this feature because it tripled our tripled our kind of rate at which we could search the backend. Our latencies were just dominated by the long tail. I should have seen that weeks ago, but didn't. I was kind of caught on some other details that I was trying to unravel. And then once I added hedge requests to the front end, we just instantly tripled the rate at which we were searching the back end by just repeating requests once they exceeded a certain threshold. So the defaults there are kind of tuned to search, which is 5 seconds for a individual job to be out, and we'll try it 3 times. So if it doesn't come back in 5 seconds, we'll just try again. If it happens again, we'll try again. And these are tuned to roughly our P99 on the search. Another feature we added was so the queries in 1.3.2 just proxy to the serverless, like we talked about, but we added a feature so the queries will actually do some work themselves. There's no reason for them just to sit there and do nothing. So search prefer self will have the querier always doing 2 jobs while continuing to proxy to the backend. It adds a little bit of throughput, and the queriers tend to have more horsepower than the serverless function, so they can churn through the jobs just a bit faster, and it helps some on reducing your latency and kind of better utilizing your queries and your resources when you're doing search. And then finally, in the ingester, we added this ability to take a step back. We've made a change in 1.4 where the range on the blocks, the time range on the blocks is based on these span times. It used to be based on ingestion time, which wasn't great. And now it's based on the span times instead. This allows us to just kind of better set the range for the blocks, especially when we replay the blocks when the ingester restarts. But the problem we found when basing on span time was people are sending us spans from like 3 weeks ago, which didn't quite work because basically every single block covered most of our retention. So any search attempted to access every block on the back end because they just said they had spans in those time ranges. So this ingestion time range slack will force the ingester to only update the block time range if it's within a certain slack time. And the main get here is when you used to replay the wall, you would basically reset those block time ranges to reset the block time ranges to be whenever the wall was replayed, which basically kind of lost them in search. With these updates, when the wall replays, it will use the span times instead, and so you won't lose those. Those will have authentic min-max time ranges, which is the kind of big get there. If you go forward. So progress so far, we fixed the min-max time range in the block, which we talked about. This will make our search more authentic. I really wanted this in cloud before we rolled it out to everybody. And we added that ingestion time range slack setting so it doesn't accept times from 3 weeks ago or something silly. We've added a new object encoding, actually only the second ever, which is increasing the rate at which we can search. So it's an improvement on 1.3.2. We've added the start and end times outside proto. One of the biggest bottlenecks in search is unmarshalling the proto and then piling through every span, looking for a specific tag key value pair, And most of this is basically just thrown away, essentially. And the cost of unmarshalling proto is quite a bit. So by putting the start end times outside the proto, we could quickly check those to see if we even need to bother with the whole trace. And so it helped quite a bit in terms of speeds. Also, we use that start end time for duration. So if you have a duration in mind and you specify that in your search, we can skip quite a few traces as well. So if you say like 1 to 2 seconds or something, anything under 1 second won't even be unmarshaled. And our current throughput at tip of main with all these improvements is about 30 to 35 gigs a second. We were only seeing like 10 to 15 gigs a second before. Occasionally we'd see like it jump to 20, and that's kind of what I was trying to unravel these past few weeks, is why we're seeing it jump to 20 sometimes. By just throwing in a hedge request and ignoring and not caring anymore why we were jumping to 20, we just immediately got 30 to 35 gigs a second, which was great. And then I have an experimental branch with some proto marshalling improvements that's seeing 60 gigs per second. 60 gigs per second on search pretty regularly, or it's consistently at about 60 gigs a second. And the improvements, unfortunately, are to use GoGo Proto, which is not maintained. So we're looking at possibly still doing that, using GoGo Proto and some features in GoGo Proto. We're also looking at Vitesse. Planet Scale has a proto marshaller that I'm working on. Actually, just today, I was spending some time getting our proto marshaled using, our proto generated using their generator. So we might try the Vitesse proto generator as well. And we're looking to get around 60 gigs a second. I think at that point, at 60 gigs a second, I'm probably going to let this rest. Maybe there'll be some small improvements, but I think we'll feel I'll be happy with those speeds as long as we can get them consistently, and then look forward to maybe the next generation of tempo backend, maybe Parquet. And we'll have the team, Marty and Ananya, talk about that a little bit about that next, and what our thoughts are on Parquet and our chances of moving there. And so to give some metrics here, at 220 megs a second, which is what we're doing internally, it takes about 20 to 25 seconds to search 1 hour. Not great, but not terrible. That's an exhaustive search. If you actually specified some parameters, it'd come back a lot faster. That is searching every single trace in the backend in that hour and failing to match anything, basically. And it's pretty stable in those time ranges, 20 to 25 seconds. Search for these larger installations for hundreds of megs a second. Search will continue to feel like a batch job for a while, but for smaller installations, double-digit megabytes a second, you could definitely see significantly faster search times, I think. Cool. And then some metrics from our serverless, if you want to go forward. Yeah, so just to share some of this because it's fun to look at. Yesterday I was, or maybe this was 2 days ago, 2 or 3 days ago, earlier this week, I was like, you can kind of see my pattern here. I'd make a small change and then run a test, and then make a small change, run a test. I was trying to unlock the combination of parameters that really helped us get to this 30 gigs a second. And so here you can see, just to share some of this is the number of instances of Google Cloud Functions when I'm doing my searches. So they're hitting like 5, 6, 7,000 instances that are active at one time. And then you can see the idle functions too. It's kind of fun to see the way Google is actually scaling down their functions after they're active. So they're active, they're doing something, and then there are no queries. And you can see how Google's kind of bringing those down, which I think is kind of a neat insight into the way they're managing their services. Next, this is the gigabytes per second as reported by GCS. So this is compressed, so it's going to be less than the 30 we were talking about, because the 30 is uncompressed proto is what I'm talking about there. So we're seeing like 10 gigs a second, spiking up to 18 gigs a second. This is coming out of GCS compressed. We are currently using LZ4 on our backend. The default is actually Z standard, but LZ4 costs less to unmarshal, so we've been experimenting with it because we're doing search. Honestly, maybe for 1.4 or perhaps 1.5, we'll probably do a revisit on our defaults. So I think in 1.2 or so, we revisited defaults and we checked kind of what we were running internally, and we brought our defaults up to what we were running internally. And I think we might do another pass at that once, maybe in 1.4 or 1.5, to make configuration easier and make things just work out of the box for large scale. But LZ4 might be the winner here on the back end. It's just way cheaper to decompress, which is a lot nicer for the serverless functions. They can, with much less CPU and memory resources, they can churn through these pages a lot faster. And then finally, this is the number of requests per second we're hitting GCS with. These are reported by Stackdriver here, but we're seeing 15,000, or I guess about 12,000 looks like average requests per second GCS is returning. And these are tiny read ranges over this block. Each of these serverless functions is slamming GCS as fast as possible to slurp out data. You can even see our polling cycle way down here, these tiny bumps. Every, I don't know, 5 to 10 minutes, you see a very small bump. That's our polling cycle, when all the different compactors are and all the different components are asking for the index JSON, or building the index JSON. So yeah, that's serverless. I'd say things are feeling good. After feeling rough in 1.3.2, I didn't really like where it was, but it was technically working. I really like where things are now. The hedge requests really added consistency to our searches. These proto improvements are going to maybe close to double the speeds we can get. I really feel like things are entering the territory where I feel comfortable with the community running it a little bit more. I feel comfortable with it being in Grafana Cloud Traces. And it's still not amazing at extremely high volume, but it's functional and usable, and I like where it is at. And then hopefully we'll look to the future for some better formats to just reduce the amount of data we pull. We're pulling just gigs and gigs and gigs from GCS to answer these questions, which is hopefully going to be unnecessary in the future. If there are any questions, feel free to hit me. If not, I can kind of hand it off to Team Future.
Hey, can we go back a couple slides to the number of active and idle instances? And I remember that being a lot lower, like that's almost 8,000. That was really cool. Was that the trick of like having multiple sets of functions and to get past kind of like the throttling?
Right. So the serverless endpoints, we actually have the ability to have more than one. And the reason is to get through past Google Cloud quotas. So Google Cloud will only have 3,000 instances of any function at one time. So we run 10, which is unnecessary. I've just been trying every combination of parameters I can to see how fast I can get data out of GCS as fast as possible. But we could probably do this with 3 or 4. And basically, this is the sum across 10 different Google Cloud functions. So, right, that's a good call. We are seeing quite a few of these functions when we run this. It's still, depending on your query load, a fraction of the cost of running Tempo as a whole, but it can add up if you sat there and just beat it to death constantly. Constant querying would cost quite a bit, but Tempo's not built for that. Tempo's built to ingest as cheaply as possible, because that's almost all you'll be doing with a tracing backend, and query in a more expensive way. It's kind of the balance that Loki takes as well. The idea being, let's make the thing that you do all the time cheap, and the thing that you do occasionally more expensive. Cool. Good insight.
Yeah, super cool. Okay, sure. Yeah, so we can talk about some backend stuff. Hey, so we actually had a couple late-minute slide changes. So either you can reload and run it, or I can share. Yeah. I can do it too. Yeah, cool. Okay, cool. Hey, yeah, so if you were here maybe or saw it a couple months ago at a community call, we kind of talked about how we had been looking into kind of a new block format for the backend, kind of like, we touched on that a lot here. And a couple months ago, it was flat buffers. We dug pretty deep into that, and we had some kind of numbers and some interesting things and findings, but ultimately didn't feel like it panned out. Since then, we've been kind of looking into columnar and Parquet in particular. So we'll kind of walk through that with just some thoughts and findings and status, and just kind of like what we're thinking there. Cool. So I'm just gonna do, yeah. So okay, so just basic stuff like why columnar. Well, we kind of touched on that, like proto buff. You have to deserialize the whole thing. Can't get past it. That's not great. Flat buffers was one way to jump around, but it didn't work out. Columnar, you only read the columns you need. So naturally, the data in our filtering, our search behavior is like very columnar. So as an example, in a 600 megabyte block, did you know that just the span IDs are 160 megs? So that's fascinating to me, because that data we never use for anything. So for searching, so why read that? Conversely, like a column we do use, span status code, we'd like to search on, is only 6 megabytes for the same number of spans. So that's really cool. So why Parquet? So there's a lot of other columnar technologies are out there. So why Parquet? Well, in particular, so it's a file, which is great. That works really well for us. So like as far as Tempo's blocks, it'd be very easy to put a file in the back end, treat it as a file. It doesn't require like heavy state or heavy installations, things like that. And it already has so many awesome things in it already, which we would want anyways. So different encodings for different data types. So delta encoding, dictionaries, run length. It has different types of compression, page statistics, so you can skip around and skip over blocks of data, bloom filters. These are all super cool. And so they all come together, make it so it's super fast, and hopefully really, you can read a lot less data. So let's go, sorry, I'm flipping around here. Okay, column design. So there's two top approaches to columns. Would you do a nested, kind of like a trace? A trace is a graph of batches, spans, attributes, things like that. Would you do that? Or could you flatten it into just a list of spans? Both options are really, really interesting. We actually tried both. And it just ended up that it seems like the nested approach is better. And it seems to come down to things that are at the resource or batch level, right? Or just flattening those down to every span just is kind of like outweighs any benefits you might get from the different designs. So examples of that are like cluster namespace pod attributes. So here's an example schema, just to kind of show like the graph, right? So you have a trace root at the top. It has a trace ID. Inside that, this is kind of matching the open telemetry line protocol. Resource spans, resource that has attributes, keys and values. Instrumentation library spans has spans, those have attributes, keys and values, and then also other attributes like start time, span name. So the actual columns in here, some of these are virtual. So the actual columns are like trace ID, the resource key, attribute, key and value, the span attributes. Cool. Okay, that's cool, but obviously like we got to go way further. There's so many cool things you could do. So one is, we want these attributes that we're searching on, don't put them all in one column. Like let's put them into their own columns. That's really cool. So so you're searching, you're just targeting a lot less data, but actually the actual block itself gets a lot more efficient because you're putting the repeated like values together into their own columns versus like keys and values. So what would that look like? Something like this, I'll highlight it. So the resource would have a dedicated cluster namespace pod container columns. These are just attributes that we commonly use in our own stuff. So yeah, and then so we can target those directly. So that would be really cool. Okay, hey Nanya, do you want to touch on these slides?
Yeah, sure. So like Marty said, we can actually blow out each of the span attributes into their own columns. And this is an example of doing that from one of our internal blocks. Like we run Tempo internally, monitor our own clusters, and this is what it looks like for one of our blocks. So under the spans thing, the field, you can see there's columns like alert ID, attempt ID block, and each of these was actually tags on the span. And we figured out a way to sort of blow these out into their own columns, and that way you can actually search for them in parallel and perform joins across them. So if you have multiple conditions in a search query, you can fire off readers for each of these columns. And each of these will be really tiny because, I don't know, a block is a couple hundred MB, and each of these could be like kilobytes. So you only end up reading like a really small section of the block. And then you can actually see the traces that match and perform joins across these columns to finally filter out the traces that match multiple conditions. So this is really cool. One of the problems that we ran into, can we go to the next slide, Marty? Was this. So when your app has auto instrumentation, you sort of end up with this bizarre schema where you have a million tags on your spans, and these get blown out into their own columns, and then it starts looking something like this. So we're trying to come up with an opinionated way of saying, hey, we're not going to blow out attributes that have a prefix that says HTTP request, or we're kind of playing around with that. We don't know what our approach is going to be, but if this turns out to be too expensive, then we might just put these into like the old way of doing it, where you just put each of these into one column. So we won't provide search on them, but you can still reconstruct the trace out of these. So this is still up in the air, but it's just something to think about. The writing of the schema gets a little expensive as we grow the number of columns, so this might help reduce that a bit. But our results are still inconclusive around that. And yeah, I think that's about it for the dynamic schemas. If we go to the next slide, I just have one last thing to point out. And all of this is possible thanks to these folks. The Segment.io team has come up with a really cool Parquet SDK for Golang, and we were able to do a lot of these things thanks to this library and the awesome work done there. So just wanted to call that out.
Yeah, this library is fantastic. It's really fast, really stable, really robust. So it's been awesome. Yeah, just a note on this. This is cracking me up because we didn't even know any of this data existed. It's funny to see it all in one place.
There's more. This is a small part of it.
Yeah, yeah.
Go back to the oh, my bad, you had some more stuff.
Yeah.
That's okay.
Go to the resource, go up one more slide. I'm shocked that that's all we have on our resource. Like, I'm not surprised there's a billion stupid tags on our spans, but I figured a resource would have a similar, like, ridiculous number of spans. It's kind of cool that it's constrained that much.
Yeah.
Yeah, I mean, I'm sure a lot of these are coming from the tracing pipeline, right? So it makes sense in some ways. Yeah, I mean, it's good. Like, it's really powerful to be filtering at that level. Yeah,
cool.
And it should work
It's
well.
also cool that we have so many languages internally, and somehow all of the SDKs have convened around these attributes, and is going to use these. Or maybe it's our internal open telemetry conversion thing. So that could be true.
Good question. I want to know who's using Slug.
Open census export version.
Right.
Plan is, I'm not sure what plan is.
Gotta have a plan.
Is that Tanka?
Who knows?
Okay.
Cool.
Yeah, okay, so we have some super early but cool benchmarks. We just wanted to share them, just to get on the hype train. So a super simple query for one cluster value and a min duration. So there's two test cases here comparing like against the original proto and the new Parquet stuff. So you can kind of see like maybe in here it's reading 600 megabytes. It's the entire block. Finding 55 traces. After converting that to Parquet, doing the same thing, we're reading 2 megabytes, same 55 traces. Super cool. It's way faster. So 22 seconds versus like this is 140 milliseconds. Yeah, so we got some cool like numbers here. Now, more realistic query, just for comparison. I actually forgot to paste in the time here, but it's like 200 milliseconds or something. But looking for all of these, and of course they're blowing out into their own columns, but like cluster namespace, pod service name, duration. So this is like kind of filtering down a lot further. We're only reading 11 megabytes. So that's pretty cool. Yeah.
That is sweet.
Yeah, so what else do we have? Okay, so there's a lot more to figure out. These are just our current findings and thoughts and our current direction. So things to figure out. Dynamic columns add a lot of moving parts, but they seem like they're worth it because it's just fantastic speeds and things like that. The results look really promising. So if you go back, we just had strings everywhere. So we need to figure out every other data type. So we have some progress on that, but there are still things to figure out. Things like you could actually have attributes of the same name but different types. So we need to figure stuff like that out. How does that even work? I'm not even sure how that would work with our current search UI. So we need to figure things like that. Parquet column naming is actually more strict than the tag names in the data. So there has to be some sort of transformation. So what would that look like? And the example is http.status code. And then just naming collision in general, that maybe it has to do with like the structure of the thing that we're creating. And of course, like the we're reading a lot less data, but the IOs are still kind of high. So that's just something we need to dig into. That's the potential thing that we need to figure out. Hey, Ananya, is there any other things that we needed to figure out? I mean, I'm sure there's tons I didn't mention.
There's also like each column can have its own compression type. So I don't know how we'll figure that out for
Oh
dynamic
yeah,
columns.
tuning. Yeah, so just tuning in general, like which encoding and compression makes sense for each column.
Yeah.
And then again, there's in writing the Parquet, there are things like row group flush sizes, like page sizes, column chunk sizes. So there's a lot of tuning like that too.
It's also slower than writing proto right now, so
yeah,
we need to figure that out. Yeah.
It's more like to create the block.
Yes, it takes longer to create the block. Although it's not in the critical path because we do it async, but it still needs to be fast. Otherwise, our rollouts will become slow. It'll just generally be a little sad.
Sure. I guess I'm not surprised, right? The proto is so dumb. It just barfs everything on disk, but this actually does a lot of work to organize the columns and do the compression, do the dictionary compression types and run length encoding compression types and all that. So we'll probably pay a little bit more on write when we move to Parquet, but the benefits, I suppose, would be definitely worth it. Not only those awesome search metrics, but I love that Parquet, if we just put raw Parquet in S3, suddenly it unlocks the ability to use any of a million tools that already exist to work with Parquet and object storage. And there's a lot of those. You can query with Athena. You could write a Flink. Is Flink a thing? Spark? One of those job things, right? I've never worked with those technologies, but you could write some of that to take your data and do anything you want with it. There's just, I think it really unlocks a world of awesomeness when we connect or use this open standard, if we can get there.
Yeah, so we're trying not to do anything horrible with the Parquet file structure that would prevent a lot of that stuff. I honestly don't know if we are. I don't think we are, but I haven't used those tools a whole lot. So
sure, we'll get
if
feedback.
If we are, please let us know.
Right.
Yeah.
Cool.
I think there's like Parquet tool visualizers and stuff that we should probably try using. Try querying the Parquet file outside of Tempo and see if
they just crash as soon as you open your file. Like, well, maybe we did something dumb. Cool. Any questions? Any concerns, thoughts? I think we've been talking about the same things for a while, but I also think we've talked about some very future things with Parquet, which is very cool. I think metrics generators coming up in 1.4 will be an awesome feature addition for anyone running it, as well as we're going to get some of those features into Grafana Cloud. I think 1.4 is going to see way better performance on search. So those of you who are using search or wanting to experiment with that are going to see far better results with 1.4. I still owe the community a guide on setting this up in AWS. Technically, we have a proof of concept running in AWS, and I have not documented this anywhere. If you do check our docs, there's Terraform for deploying to Google Cloud, but nothing for AWS. So I do owe you all better documentation on the serverless path, as well as some specific docs around how to get this running with Lambda, AWS Lambda, and S3. But other than that, I think we're cool. All right. Well, thanks for another good community call. I will catch you all next month. Grab us in Slack, throw some issues in the GitHub repo. Yeah, connect to us however you feel most comfortable. And thanks for using Tempo, and we'll catch you next month. See y'all.
Yeah.
Okay, cool.
See ya. Thank you.